Hi, it's me, Dr. Prasad Puthiyillam, continuing my classes on coordination chemistry, class number 12. I'll be explaining the Curie Law and Curie-Weiss Law and continuation of that, ferro and antiferromagnetic coupling. Curie or Curie-Weiss Law. So the susceptibility of different kind of magnetic materials are distinguished by their different temperature dependence as well as their absolute magnitude. Many paramagnetic substances obey Curie law, especially at a high temperature. This can be defined, or this state in which the magnetic susceptibility is inversely proportional to temperature is known as Curie's law, or chi is equal to C by T, where C is the Curie constant. But often, some of the experimental data, if you observe, you can see that that is not fitting the Curie law. Therefore, a new law was introduced, Curie-Weiss law, which says that chi is equal to C divided by T plus theta, where theta is the Weiss constant. So the Curie law and Curie-Weiss law are graphically presented here with 1 upon chi versus T. The Curie-Weiss law shows a straight line passing through the y-axis and touching the x-axis at a point theta, whereas Curie law, it passes through the origins. So for ferro as well as antiferromagnetic substances, the temperature dependency of magnetic susceptibility does not fit even the Curie-Weiss law as such. So the MH curve of the magnetic materials like ferromagnetic, ferrimagnetic, paramagnetic, antiferro and diamagnetic materials are represented here, and the chi inverse versus temperature, which shows that paramagnetic substances are almost obeying the Curie-Weiss law, whereas antiferromagnets are deviating. Even the ferromagnets are also deviating from that. So it introduces to critical temperature known as Tc, which corresponds to ferromagnet critical temperature, and Tn, Neal temperature, which corresponds to the antiferromagnets. So the susceptibility versus temperature graph, it shows that paramagnetic behavior, ferromagnetic behavior, as well as antiferromagnetic behavior. So the ferromagnetic substance show a very large susceptibility at a low temperature, and it decreases with the increasing temperature. Okay, initially we can see there is a larger susceptibility value, but gradually, or in a fast rate, it is decreasing. And after Curie point, it obeys, the ferromagnets obeys Curie-Weiss law, but below that critical point, critical temperature, it is not obeying the Curie-Weiss law. Above a certain temperature, that is Tc, it is no longer ferromagnetic, but it behaves as paramagnetic, and it obeys the Curie-Weiss law. For antiferromagnetic, the material under antiferromagnetic material, the value of chi is actually increases with the rising temperatures. You can observe here, it is initially increasing till the Neal point. So the temperature is known as Neal point, or Tn, and above Tn, the material again reverts to paramagnetic behavior. Above Tn, it behaves as paramagnetic. The paramagnetic, these type of behaviors, it needs explanation. Therefore, the explanation is given here. In case of paramagnetic substances, the chi value corresponds to the situation where unpaired electrons are present in the material and show some tendency to align them in magnetic field. So due to the presence of unpaired electrons, we call them as the paramagnetic behavior. And as we know, as we increase the temperature of any substance or almost any material, almost all material, as we increase the temperature, the thermal energy will be increased of the ions or electrons present in the material. Their thermal energy will increase. It starts getting extra energy to vibrate or to change their direction of arrangement. So this is a natural tendency uh, which increases the disorderedness in the material. Therefore, as the temperature increases, it causes the disorder in the arrangement of temperature. Therefore, a paramagnetic material, the thermal energy of ions and electron acts partially cancel the ordering effect of the applied magnetic field. Therefore, as paramagnetic material, the magnetic susceptibility value decreases with the increase in temperature in Curie or Curie-Weiss law fashion. In case of ferromagnetic material, the electron spin are aligned parallel to to each other. That is due to the cooperative interaction or the interaction between the neighboring magnetic domains, and they are all the spins are arranged in a parallel fashion, and when they are all arranged in a parallel fashion in a magnetic field, they will sum up. So it is represented here when they are parallel fashion in presence of magnetic field, it gives a higher value. The sum total of the spin behavior gives the value. Therefore, in case of ferromagnetic material, initially we have a higher magnetic susceptibility value, and this is affected by or controlled by the magnetic field as well as temperature. So we need a high magnetic field as well as low temperature to have this type of behavior where the spin natures are added up and we are getting a higher spin value. For ferromagnetic material, the increasing temperature creates disorderness in the alignment of spin, thus decreasing the chi value. That means as the temperature is increased, this arrangement it get disturbed, which are arranged already in parallel fashion. Some of the alignment will get disturbed, or all material will not be arranged in the same manner. That is the effect of temperature. Therefore, the magnetic susceptibility value is decreasing in case of a ferromagnetic material. In case of antiferromagnetic material, the electron spin are aligned anti-parallel and have a cancellation effect on the magnetic susceptibility. Hence, smaller chi value, that is magnetic susceptibility values, are expected in case of antiferromagnetic, because they are cancelling each other. They are opposite each other and total effect is zero or near to that. Therefore, we can say that initially the antiferromagnetic substances, the susceptibility value is very less. But as the temperature increases, some of the spin value which are anti-parallel will be arranged or aligned parallel to each other, or they become parallel in the initial cases. Therefore, that may causes for the increase in the susceptibility value for antiferromagnetic materials up to nil point. Now, ferro and antiferromagnetic coupling. The spontaneous alignment of magnetic dipoles in a ferromagnetic or antiferromagnetic state, that is due to the positive energy of interaction between the neighboring spins, either it is in a parallel fashion or anti-parallel fashion. The origin of this coupling or the cooperative interaction, it can be explained only with a quantum mechanical phenomena, not with a classical phenomena. According to the classical phenomena or classical electromagnetism, two nearby magnetic dipoles will tend to align in opposite directions. The process by which the coupling of spins occurs and give rise to antiferromagnetism. Say example in case of NIO or MNO, that can be explained as a super exchange. So super exchange, it is antiferromagnetism occurs through intervening ligand, even the presence of a ligand. So I took the example of NIO here. The ligands, presence of ligand also, some of the the electrons present in the metal, the cation, that will be exchanged such a way that it becomes antiferromagnetic type. So for MNO, NIO is an example for such material which shows this antiferromagnetic coupling. So this super exchange, it is also known as Kramers-Anderson super exchange. It is usually strong antiferromagnetic coupling between two next to nearest neighbor cation through a non-magnetic anion. So here example is given with manganese Mn. Mn2 Mn ions are present here, or atoms, the metal are present near to each other, in between oxygen is also present. So in this way it differs from the direct exchange in which there is a coupling between nearest neighbor cation involving an intermediate anions. If you take the example of NiO, the Ni2 plus ion has 8 d electrons, and if they are arranged in a octahedral fashion, uh, the arrangement of the metal ion is in the crystal lattice, if it is octahedral shape, the two of these electrons are singly occupied, that is the EG state orbitals, that is dz square and dx square to y square. Therefore, these two singly occupied electrons are represented here, and this is the electrons present in the p orbital of oxygen. The orbitals are oriented so that they parallel to the axis of unit cell, and therefore point directly at the adjacent oxide ion, and the unpaired electron in the Eg orbitals of Ni2 plus ions are able to couple magnetically with the electrons in the p orbitals of O2 minus. The p orbitals of the O2 minus ion contain two electrons each, which are coupled anti-parallel. They are arranged in an anti-parallel fashion. And hence, if the Ni2 plus and O2 minus ions are sufficiently closer to each other, that the coupling of the electron is possible, and this happens in a chain fashion. Next Ni molecule, next oxygen O2 minus, it can further couple with Ni in an anti-ferromagnetic ordering fashion. So that is in case of antiferromagnetic coupling. Ferromagnetic coupling, the property of ferromagnetism, it is due to the direct influence of two effects from quantum mechanics, namely the spin effect as well as the Pauli's exclusion principle. In many materials, the electrons come in pair of opposite spin, which cancel one another's dipole moment, and only atoms with unpaired electrons can experience a net magnetic moment from the spin. A ferromagnetic material has many such electrons, and if they are aligned, they create a measurable macroscopic field. So in a ferromagnet, however, they tend to align in same direction because of the Pauli's exclusion principle, which states that no two electrons with the same spin cannot lie in the same position, and which feels an effective additional repulsion and lowers their electrostatic energy. So the difference in energy is called the exchange energy, and induced nearby electrons to they allow the electrons to align in that fashion. So in case of ferromagnetic coupling, both the spin as well as Pauli's exclusion principle we need to consider, that creates the ferromagnetic coupling. Hope you understood the concept of Curie's law, Curie-Weiss law, and how it affects the paramagnetism, ferromagnetism, antiferromagnetism, and ferro and antiferromagnetic coupling interactions. Thank you very much for watching my video, and have a nice day.